Welcome to the second set of 10 problems for the Physics GRE GR0877. So glad to have you here. Let's continue. So number 11, a quantum mechanical harmonic oscillator has an angular frequency of W, the omega, we're going to call it W. The Schrodinger equation predicts that the ground state energy of the oscillator will be. So the quantum mechanical harmonic oscillator energy equation is E equals h bar w times the quantity n plus 1/2. That 1/2 is very important. So for n equals 0, 1, 2, 3, dot, dot, dot. In our case, the ground state is going to be n equals 0. So plug that into our energy equation above. So E equals h bar w times the quantity 0 plus 1/2. N equals 0, 0 is our ground state. So the ground state energy is going to be 1/2 h bar W, and that is answer C. Number 12, in the Bohr model of the hydrogen atom, the linear momentum of the electron at radius Rn is given by which of the following? N is a principal quantum number. So in the Bohr model of the atom, the angular momentum equals mvr, and that equals nh bar. So we all know linear momentum equals mv, which is our mass times velocity. So we're going to do L, which is angular momentum, divided by R, which should equal our linear momentum. That equals mass times velocity, so that just simply equals nh bar over R. That is answer C. Number 13, the figure above represents a log-log plot of variable y versus variable x. The origin represents the point x equals 1 and y equals 1. Which of the following gives the approximate functional relationship between y and x? So notice that our plot starts at not 0, 0, but 1, 1. So let's just pick up any point. The first point is going to work best. It's roughly at x equals 3, 1, 2, 3, y equals 10. And so the functional relationship must satisfy these coordinates, specifically this one. So let's plug in these values to each answer and just see which one works. It's the easiest way to do this. So for A, y equals, well, y is 10, so it does 10 equals 6 times the square root of 3. Yes, about 10.39 it does. Let's just keep going to C, though. So number B, y equals 1/2 x plus 6, so 10, does that equal 1/2 x? X is 3, so that's 1.5 plus 6, so does 10 equal 7.5? No. And you can just keep going down. They're pretty easy to go down and figure out that answer A is your correct answer, and that's to be the one that gives you y equals about 10. Number 14, two experimental techniques determine the mass of an object to be 11 plus or minus 1 kilogram and 10 plus or minus 2 kilograms. These two measurements can be combined to give a weighted average. The uncertainty of the weighted average is equal to which of the following? So we have our equation up here for the uncertainty and the weighted average. And so that's going to equal 1 divided by sigma 1 squared plus 1 divided by sigma 2 squared. That quantity in the denominator, square root. So let's plug in our numbers for the uncertainty in the mass of the object. So 1 divided by 1 squared plus 1 divided by 2 squared, that quantity squared, square root. So just take it through and you can see that the uncertainty equals 1 divided by 5 divided by 4th, quantity square root. So the 4 is, you can take the square root of that. It's the denominator. For denominator, move it upstairs. The square root of 4 is 2. It goes upstairs. We still have our 5 in the denominator. And that just simply equals 2 divided by the square root of 5. That is answer B. Number 15. This is a fun one. This is, let's see, the lens maker's equation. If the 5 lenses shown below are made of the same material, which lens has the shortest possible focal length? So the lens maker equation is above right here. So F is the focal length, R1 equals the radius or curvature of the closer surface, R2 equals the radius or curvature of the further surface, D equals the thickness of the lens, N equals the refractive index. So we can set N to really any number we want besides N equals 1. So let's just set it equal to 0. So 1 divided by f, the focal length, equals -1 over r1 plus 1 over r2. So, and that follows from the equation above. For r1 equals 0, the focal length equals plus or minus r2. If r1 equals minus r2, remember we're going to do positive curving to the right, negative to the left. Then for a, 1 over the focal length is going to equal minus 1 over r1 plus 1 over minus r2, and that's going to equal minus 2 over r equals 1 over f. So the focal length is going to equal minus r over 2. Okay? It must be positive according to the question, so we can rule that out. For D and E, 1 over the focal length equals minus 1 divided by minus r1 plus 1 over r2 equals 2 over r equals 1 over f equals f divided by so the focal length f equals r divided by 2. Since r in answer E is smaller than r in answer D, E is going to be correct. Now, let's talk for just a second about the radius of curvature. So, somewhat counterintuitively, but when you think about it, it makes sense. The radius of curvature, so things with a small radius have a high radius of curvature. So you can see the inside circle here has a smaller radius, but it has a larger radius of curvature. And the larger circle has a larger radius, but a smaller radius of curvature. Again, here's another really nice example here. You can see the smaller circle's radius of curvature is right here. You can see the larger circle, the larger radius, its radius of curvature right here, and you can clearly see that the radius of curvature for the larger circle is smaller than the radius of curvature for the smaller circle. And so we want the thing that has the larger radius between D and E. E has obviously a larger radius than D, so we are going to go with answer E. Number 16, unpolarized light is incident on a pair of ideal linear polarizers whose transmission axes make an angle of 45 degrees with each other. The transmitted light intensity through both polarizers is what percentage of the incident intensity? So unpolarized light through the first filter is reduced in intensity by 50% when it passes through. So I1 equals 0.5 times IO. So the law of malice, when the second polarizer is rotated by an angle theta to the first polarizer, I2 equals I1 cosine squared theta. Okay, so I1 in our case is I2 in our case is going to equal I1 cosine 45 degrees times cosine 45 degrees. Cosine of 45 degrees, you kind of got to know our unit circle. It equals, we'll get into that later as well throughout the exam, 0.707 is the cosine of 45 degrees. So that quantity squared times I1. And so then in terms of IO, I2 equals 0.5 IO times 0.707 squared. 0.707 squared is 0.5, so 0.5 times 0.5 times IO equals 0.25, the initial intensity. And so that is answer D. Number 17, a very long, thin, straight wire carries a uniform charge density of lambda per unit length. Which of the following gives the magnitude of the electric field at a radial distance r from the wire? So we're going to use Gauss's law and integral of infinitesimal point charges since it's a very long, thin, and straight wire. So phi is going to equal q over epsilon, q being the charge. Phi equals lambda L, which is our linear charge density, lambda L divided by epsilon, and that is going to equal the electric field times 2 pi r L, where 2 pi r L is the volume of a cylinder surrounding the wire. So lambda L divided by epsilon equals the electric field times 2 pi r L. So therefore electric field E equals lambda divided by 2 pi r times epsilon. And that is answer A. Number 18, the bar magnet shown in the figure above is moved completely through the loop. Which of the following is a true statement about the direction of the current flow between the 2 points A and B in the circuit? So let's draw some coordinates on this to get our bearings. So notice the south pole is entering first, so we know the magnetic field must be entering into the south pole. Magnetic fields enter into the south pole, enter out of the north pole. We can draw those also. They enter They exit out of the North Pole, curve around, and enter into the South Pole. So we know that, and then again, let's draw, again, this is going to be the x positive direction is going to be that way, and then the x negative direction is going to be that way. And then so the y direction, that's going to be the positive y direction, and then perpendicular is going to be, that is going to be the z negative direction, and coming this way will be the z positive direction. And then of course going down will be the y negative direction. So we want to start off with Lenz's law. The EMF induced produces a magnetic field whose magnetic field opposes the change which produces it. So again, we're noticing that the south pole enters the loop first. Magnetic fields enter into south poles, therefore using the right-hand rule, you know the direction of the magnetic field of the magnet, which is the negative x direction, as well as the force, the positive y direction, and the current, the negative z direction. So the negative z direction would be from A to B. But the induced current must produce a force that goes in the opposite direction of the magnet's force. So using the right-hand rule, on the way in, the induced current would travel in the opposite direction of above, so it would be from B to A. And then on the way out, the magnet moves completely through the loop. So therefore, the North Pole exits first on the way out, so the force is therefore reversed. And using the right-hand rule, so is the induced current when the magnet moves out through the loop. So the induced current would therefore move in the opposite direction as above. So on the way out, it would move from A to B, and that is answer E. Number 19, the surface of the sun has a temperature close to 6,000 Kelvin, and it emits a black body Planck spectrum that reaches a maximum near 500 nanometers. For a body with a surface temperature close to 300 Kelvin, at what wavelength would the thermal spectrum reach a maximum? So we're going to apply Wien's law, where lambda max equals B over T, T being the temperature, and where B is Wien's constant, which is 2.9 times 10 to the minus 3 in a particular set of units. So we can simply say that lambda 1 T1 equals lambda 2 T2, and therefore lambda 2 is going to simply equal lambda 1 T1 divided by T2. So plug in your numbers, and that comes out to be 104 nanometers, which is 10 micrometers. Refer back to your chart on the cover page for those units. So that is going to be answer A. Number 20, at the present time, the temperature of the universe, i.e. the cosmic microwave background radiation, is about 3 Kelvin. When the temperature was 12 Kelvin, typical objects in the universe, such as galaxies, were. So every young cosmologist knows this, I'm sure, by heart. The temperature of the universe scales inversely with the scale factor A. And so A, the scale factor, you can kind of in a simplified way think of as the radius of the universe. So the temperature is going to scale inversely with that. So we can simply say that T1A1 equals T2A2. And so 12 Kelvin times the scale factor divided by some number equals 3 Kelvin times the scale factor. And so with some simple algebra, you can see 12 Kelvin divided by 4 would give us 3 Kelvin. So the scale factor divided by 4 means that objects in the universe were about 1/4 as distant as they are today. Okay, that was another set of 10. I'll see you next time.